Welcome to this lecture. Today we shall be discussing the evolution of massive stars. Stars, say, between 10 times the mass of the Sun to about 25 or 30 times the mass of the Sun. This is the Hertzsprung-Russell diagram, which I have shown many times. The luminosity of the star increasing vertically along the y-axis, and the surface temperature of the star increasing as we go from right to left on the horizontal axis. This band of stars is the zero-age main sequence of stars. In the previous two lectures, we considered the evolution of low-mass stars as well as the intermediate mass stars. Today we shall focus on the massive stars. This is the nuclear cycle that I have mentioned many times before. There is a certain fusion reaction. Some element is being fused to a heavier element. That element gets exhausted, and the newly formed element is inert because the core isn't hot enough to ignite the ashes of the first stage of nuclear reactions. Therefore, gravity will compress the core, and the core will get hotter, and at some stage it will get hot enough for the next stage of fusion reaction to start, and so the many acts of the stellar drama will continue as shown in this diagram. As I have said already twice, and let me repeat it, the temperature needed to fuse an element depends upon the charge of the two nuclei. Greater the charge, greater the Coulomb repulsion, and therefore higher the temperature that will be needed. Hydrogen will fuse to helium very comfortably at a temperature of about 10 million degrees. The central temperature of the Sun is 15 million degrees, and so there is no problem whatsoever. But for helium to fuse to carbon and oxygen, you need a temperature of 100 million degrees. And for carbon to fuse, one needs a temperature of 500 million degrees. And for oxygen to fuse, one needs a temperature of 10 to the 9 Kelvin. Now the question is the following. As the nuclear reactions proceed, is it going to be a quiescent fusion reaction, or is it going to be a runaway reaction resulting in a violent stellar explosion? That is really the question. A fusion reaction will be quiescent or controlled if there is a safety valve. In other words, if by chance you produce some extra energy, the system will come back. On the other hand, there will be a runaway reaction resulting in a violent stellar explosion if there is no safety valve. Now, if the stellar drama was allowed to continue through its many acts, then just before the final act of the drama, if you were to go and look right at the center of the star, what you will find is a very small core which will look like an onion with many layers. Right at the center, there will be an inert iron core. Surrounding that, silicon will be still being converted to iron, and so on, till finally in the outermost skin of the onion, hydrogen is still being converted to helium, and out there you have millions and millions of kilometers of gaseous star. But whether or not the nuclear cycle proceeds all the way till iron is produced right at the center depends upon whether the core remains an ideal gas or not. As I have explained in the previous two lectures, if the fuel ignites in a degenerate core, then it will result in a stellar explosion. Let us remind ourselves of the safety valve if the gas obeys classical equation of state, namely Boyle's law. I have a star with a core at a temperature T and has a pressure P, which is given by Boyle's law. And for some reason, I increase the energy production in the core. This will result in the core heating up to a temperature T plus delta T. Now, because the gas in the core obeys Boyle's law, if I increase the temperature, then the pressure of the gas will increase. It has to increase because the pressure is nKT. Now, therefore, when T becomes T plus delta T, the pressure will become P plus delta P. Now, here the core was in hydrostatic equilibrium. In other words, the pressure gradient was balanced by the gravitational force due to the mass interior. But now, if the central pressure increases, this hydrostatic equilibrium is disturbed and the core will expand. And as the core expands, the core will cool. And as the core cools, the energy production rate will decrease. And the core will contract. And so we are back to where we started. So this is the safety valve that exists in a star as long as the material in the center of the star obeys Boyle's law. On the other hand, if the material in the center of the star is degenerate and obeys Fermi-Dirac statistics, then the situation is very different. Let us consider the core at a temperature T and pressure P, and let us increase the luminosity. The core will get hotter, but the pressure will not increase because for a quantum gas, the pressure has nothing whatsoever to do with temperature. And because the core has got hotter, the nuclear reactions will proceed even faster. And that will increase the luminosity. And that in turn will make the core hotter, and the nuclear reaction will proceed even more furiously. And there will be a runaway reaction. So let me remind you once again that for a degenerate Fermi-Dirac gas, the pressure is decoupled from temperature. So the pressure remains the same, but the temperature continues to increase, and that results in a runaway thermonuclear reaction leading to the stellar explosion. Therefore, whether or not the stellar drama proceeds to the final act depends upon whether or not there is a safety valve, which in turn depends upon whether the core obeys classical equation of state or not. Now, what is the ideal gas pressure? That is given by Boyle's law. The pressure of the gas is nKT, where n is the number of particles per unit volume. I have now written the number in terms of the mass density rho. So clearly, if I divide the mass density by the mass of the individual particle, then I will get the number density of particles. Here mu is the mean molecular weight that tells me how to convert number density of particles to mass density. Please remember, all particles contribute to the pressure, the electrons, the protons, and the neutrons. But the mass is essentially contributed by protons and neutrons. The mass of the electron is negligible. And to allow for that, one introduces the mean molecular weight. If you know what it is, it's fine. If you don't know, just ignore it. So I just say that I divide the mass density by the mass of the proton, then I'll get the number of particles. The degeneracy pressure, on the other hand, is given by density to the power 4 by 3. We had derived in the lecture on Fermi-Dirac statistics that the degeneracy pressure is proportional to the number density to the power 4 by 3. I have written the number density in terms of the mass density by once again dividing the mass density by the mass of the elementary particle, and K is the constant of proportionality. So these are the two pressures calculated according to classical physics and quantum physics. Now, whether or not the gas behaves classically or as a degenerate Fermi gas depends upon the following. As long as kT is much greater than the Fermi energy EF, then the gas will be classical. But if the Fermi energy is much greater than kT, the thermal energy, then the gas will have to obey Fermi-Dirac statistics. And the transition occurs when the Fermi energy and the thermal energy kT are roughly comparable. So, let us return. The key question is the following. At the end of every stage of the nuclear cycle, the core is inert. When I convert hydrogen to helium, the helium core is inert till it becomes hot enough. When I convert helium to carbon, the carbon core is inert till carbon is heated to 500 million degrees and so on. Till then the core is inert and therefore it will contract. Now if the gas obeys classical statistics, then if I compress the gas, it will get hotter. Remember the adiabatic relation, T rho to the power 1 minus gamma is a constant. Now the question is, will the core remain classical, described by Boyle's law, or will the core become quantum mechanical, described by Fermi-Dirac statistics? This is the question. If the core remains classical, then the nuclear reactions in the successive phase of the nuclear cycle will be quiescent, and you will go all the way up to the synthesis of iron 56 right at the center of the star. But if along the way, in one of the acts of the stellar drama, the core becomes degenerate and gets hot enough and ignites, then the star will blow itself up, and it will never get to the stage where iron is produced at the center. Whether or not the core will remain classical was answered by Chandrasekhar in a very famous paper in 1932. He was only 21 years old at that time. In my very humble opinion, this is perhaps the most profound paper he wrote in that phase of his career. In fact, it's even more profound than the paper for which he is most famous and for which the Nobel Prize was awarded many years later. Now, let us now try to understand what Chandrasekhar showed in this extremely prescient paper. The total pressure of the gas in the core is the sum of gas pressure and radiation pressure. Miss Eddington introduced radiation pressure in 1923. Gas pressure is given by Boyle's law, and radiation pressure is given by Stefan's law. In a star like the Sun, radiation pressure is only about 8 or 10% of the total pressure. Therefore, you can almost ignore radiation pressure. Gas pressure is the dominant pressure. But as I said in the third lecture, one of Eddington's important insights was that the fraction contributed by radiation pressure to the total pressure will be more and more significant as we go to more massive stars. In other words, as we go to more massive stars, this radiation pressure becomes more and more of a contributor till finally in very massive stars, radiation pressure is far more important than gas pressure, exactly the opposite of what obtains in a star like the Sun. In a star of say 15 or 20 solar mass, gas pressure will be extremely unimportant. So it will be a competition between gravitational pressure and radiation pressure. When we first set up the equation of hydrostatic equilibrium, a la Lane, Kelvin, Emden, and so on, it was a competition between gravity and gas pressure. Then Eddington came along and said it is gravity versus gas pressure plus radiation pressure. Now what I'm saying is that in very massive stars, it is essentially a competition between gravitational inward pull and outward directed radiation pressure. Gas pressure is very insignificant. Now what Chandrasekhar discovered in this historic paper of 1932 is that if the radiation pressure exceeds 9.2% of the total pressure, then matter will never become degenerate, no matter how high the density will be. Remember, as the density increases, the Fermi energy increases as density to the power 2 by 3. So all along we have been saying that yes, initially kT may be greater than EF, but as the core is compressed, the density will increase, the Fermi energy will increase as density to the power 2 by 3. At some stage, the Fermi energy becomes much larger than kT, and the gas becomes degenerate. This is what we found in low mass stars. This is what we found in the intermediate mass stars. But what Chandrasekhar showed in this paper is that if the radiation pressure exceeds 9.2% of the total pressure, then matter will never become degenerate, no matter how high the density may become. The Fermi energy will never become greater than the thermal energy kT. And I would like to stress that this is an exact mathematical theorem. Now let us say this pictorially. What I have here, stars of various masses increasing from left to right. What I have is gas pressure here, what I have is radiation pressure here. What I have said so far is that gas pressure is more important fraction in low mass stars, whereas radiation pressure is more important in more massive stars. There is a critical mass. This is what Chandrasekhar's theorem states, is there is a critical mass of the star below which radiation pressure is less than 9.2% of the total pressure. Therefore, below this critical mass, the mass of the gas in the core, upon compression, will become degenerate. But on the other hand, if you consider stars with masses greater than this critical mass, then radiation pressure in all these stars will be greater than 9.2%, and therefore this cores of all these massive stars will remain classical and obey Boyle's law, no matter how high the density is, and therefore you will be guaranteed a safety valve. And therefore, all stars above this critical mass, for all stars above the critical mass, the many act of the stellar drama will proceed without any catastrophic stellar explosion till in the end iron is produced right at the center of the core. So, to repeat once again, we said the question is whether the gas obeys classical statistics or quantum statistics. We said that depends upon a competition between kT and EF. If kT is much greater than EF, then it will be classical. On the other hand, if EF is much greater than kT, it will be quantum mechanical. So this is certainly one way of comparing the two situations, namely the classical situation and the quantum situation. You can state the condition for the gas to remain classical or ideal in a different way. You can say the stability of the core depends upon the balance between the pressure of the gas and the gravitational pressure. A gas will obey the ideal gas law if the numerical value of the pressure calculated from Boyle's law is greater than the degeneracy pressure calculated from Fermi-Dirac statistics. In other words, what I'm saying is instead of calculating the characteristic thermal energy kT and the characteristic quantum energy and comparing them, we can also calculate the pressure according to the classical formula and the pressure according to the quantum formula and see which is greater. It's the same thing. So what Chandrasekhar chose to do was to compare the pressures. And the statement is, as long as the pressure of the ideal gas, pressure calculated according to the ideal gas formula, namely Boyle's law, as long as that pressure is numerically larger than the value of the pressure calculated from Fermi-Dirac statistics, then the gas will remain classical. So that's the condition. So now what we are going to now say is that we shall be concerned mainly with electrons because the pressure of the electrons is much greater than the pressure exerted by the nuclei. Remember, I had stressed this when we discussed Fermi-Dirac statistics. The pressure of an ideal classical electron gas is given by nkt. It can also be written as rho kt divided by mu mp, where rho is the mass density and n is the number density. We have written the number density n in terms of the mass density. Mu is the mean molecular weight of the electrons. What is the mean molecular weight of the electrons? Please remember that for every electron, if you leave out hydrogen, for all the elements in the periodic table other than hydrogen, for every electron, there are two massive particles in the nucleus. You take helium nucleus. It has 2 protons and 2 neutrons, and you have only 2 electrons. In other words, the ratio of capital Z divided by capital A, which is the ratio of the nuclear charge to the nuclear mass, is roughly 1/2 for almost the entire periodic table after hydrogen. So this mu is simply to allow for that factor. The ideal gas pressure is a function of both density and temperature, whereas the degeneracy pressure is a function of only the density. The temperature does not come into the formula at all. So we have a difficulty in comparing ideal gas pressure with degeneracy pressure because we'll be comparing apples and oranges. This is the function of density and temperature. This is the function of only density. You can only compare apples with apples and oranges with oranges. And there is a little trick that you can do that. So, as I said, a gas will obey ideal gas law if the pressure calculated according to Boyle's law is greater than the pressure calculated from Fermi-Dirac statistics. Ideal gas pressure depends on both density and temperature, whereas the degeneracy pressure depends only on density. So how do I compare the two? This is an apple, this is an orange. So you can do that by adopting a little trick. It's a very simple trick. Let us introduce a fraction beta. It's a number. It's a fraction that goes from 0 to 1. How is this fraction defined? This is just a trick to express the gas pressure in terms of the density and this fraction beta instead of density and temperature. I said you can't compare apples with oranges, but I'm trying to make the apple look like an orange so that I can compare this orange with this orange. So what I'm going to do is the ideal gas pressure is a function of density and temperature. Instead of that, I'm going to write it as a function of density and this fraction beta. How do I do that? It's very simple. How do I define the fraction? The fraction beta is defined as follows. Beta times the total pressure is the gas pressure. Therefore, 1 minus beta times the total pressure is the radiation pressure. Therefore, beta is the fraction of the total pressure contributed by gas pressure, and 1 minus beta is the fraction contributed by the radiation pressure. So by changing beta, I can make gas pressure more or radiation pressure more. So here is the total pressure is a sum of gas pressure plus radiation pressure. That's what I have written there. Total pressure is sum of gas pressure and radiation pressure. Instead of writing that, I have written total pressure as 1 over beta times gas pressure. But total pressure is also 1 minus beta times radiation pressure. There are no tricks here. Now let us look at these two terms here. I've rewritten it. So 1 over beta times rho kt over mu mp is equal to 1 over 1 minus beta times 1 by 3 at to the power 4. I have not done anything so far. I've just introduced a fraction beta. Now I can solve this equation for the temperature in terms of rho and beta. If I solve for that, I get temperature is what is given in the square bracket multiplied by rho to the power 1 by 3. So what I have done is express the temperature in terms of beta and rho. So I can use this expression in Boyle's law, which says the gas pressure is rho kt. Instead of T, the temperature, I can use this expression on the right-hand side, because I have expressed temperature in terms of the fraction beta and in terms of the mass density rho. So that is done in the next slide. So this is the same thing as in the previous slide. By introducing this fraction beta, which is the fraction contributed by gas pressure to the total pressure, and 1 minus beta is the fraction contributed by radiation pressure to the total pressure. Now, I take this value of T, this expression for T, and substitute it in the ideal gas expression for the pressure of the gas. So the pressure of the gas is rho kt by mu mp. This is simply Boyle's law. Boyle's law is a function of both the density as well as the temperature. Now, I don't want temperature because I want to compare it with an apple or with an orange, which is only a function of density. So I have written temperature in terms of beta and rho, and I will get the expression for the ideal gas now reads as the square bracket to the power 1 by 3, rho to the power 4 by 3, which I shall call some function of beta times rho to the power 4 by 3. The C of beta is the square bracket. A is Stefan's constant, K is Boltzmann's constant, mass of the proton, 1 minus beta is the fraction contributed by radiation pressure, and beta is the fraction contributed by gas pressure. Now, if classical pressure of the electron is greater than the degeneracy pressure, then the gas will remain classical. This is what I've been saying many times. So gas pressure is now been recast in this form. It is a function of this fraction beta and rho to the power 4 by 3. Let me stress, no fraud has been committed. All I have done is to express temperature and Boyle's law in terms of the density and this fraction beta. The degeneracy pressure is a function of density only. So I have now cast the gas pressure in terms of density and beta. Degeneracy pressure is rho to the power 4 by 3. So this apple has now been cast as a modified orange, and this is an orange. So I can compare oranges and oranges because both involve only dependence on density. So now I can ask the question, what is the condition that the pressure of the gas calculated according to Boyle's law will be greater numerically than the pressure calculated according to Boyle's law. In other words, what is the condition? That this thing over there is greater than this thing over there. C is given by all these things inside the square bracket to the power 1 by 3. This is what Chandrasekhar did in the paper of 1932. So the condition that classical pressure is greater than the quantum pressure is that this left-hand side must be greater than this constant K2, which comes in the degeneracy pressure. Degeneracy pressure is K2 times rho to the power 4 by 3. Now, this can be solved because I know the value of Stefan's constant, the mass of the proton, Boltzmann's constant, and so on from Clark's tables. So this can be solved, and I get a very simple relation that if 1 minus beta is greater than 0.092, then the gas will remain classical, irrespective of how high the density will be. What does 1 minus beta greater than 0.092 means? It means that as long as radiation pressure is more than 9.2% of the total pressure, then the gas will remain classical. So, if the radiation pressure is greater than 9.2% of the total pressure, then degeneracy will not set in at all, no matter how high the density becomes. So this is the conclusion of Chandrasekhar's remarkable paper. If radiation pressure exceeds 9.2% of the total pressure, then matter will never become degenerate, no matter what the density is. Therefore, stars above a critical mass will never become degenerate, and therefore the safety valve can be taken for granted during the various stages of nuclear cycle. Now, so let's go back to this. We said that gas pressure is more important in low mass stars, radiation pressure is more important in more massive stars. There is a critical mass below which the radiation pressure is less than 9.2%, and therefore if I compress this gas at some stage or other, it will become degenerate or quantum mechanical. On the other hand, for all stars with mass greater than a certain critical mass, radiation pressure will always be greater than 9.2% of the total pressure, and the core will remain classical no matter how high the density will be. So one picture is worth 10,000 words. So let us look at this graphically in case you didn't like the algebra that I did. Because what I want you to remember is the message and not this extremely elementary algebra. So what is plotted on the y-axis is the logarithm of the pressure increasing vertically and the logarithm of the density increasing horizontally along the x-axis. There is a line which is a line of demarcation between classical behavior and quantum mechanical behavior. If you are to the left of the line, then the gas is classical, but if you are to the right of the line, then the gas is quantum mechanical, and as long as you are at a density less than about 10 million grams per cubic centimeter, then the gas will be non-relativistic. In other words, the velocities will be small compared to the speed of light. But on the other hand, if I go to higher density, then the gas will be degenerate, but it will now be relativistic. In other words, the speeds of the particle will be comparable to the speed of light. So this entire region to the right in the density versus pressure diagram, gas is quantum mechanical. To the left, the gas is classical, and it obeys ideal gas law, which is given by nkt, which I have cast as C of beta multiplied by rho to the power 4 by 3 by introducing this fraction beta and 1 minus beta. Beta is the fraction contributed by gas pressure to the total pressure, and 1 minus beta is the fraction contributed by radiation pressure. to the total pressure. So beta plus 1 minus beta is 1. So let us consider the situation where radiation pressure is only 2% of the total pressure. In other words, 1 minus beta is only 2%. In other words, gas pressure is 98%. So something like the sun, for example. So what you find is that as long as the density is below this arrow over there, pressure calculate, what is plotted as the black line is the value of the pressure calculated according to Boyle's law as a function of density. What is plotted as the blue line is the pressure calculated according to Fermi-Dirac statistics, rho to the power 5 by 3 and rho to the power 4 by 3 for relativistic particles. So you see that if the radiation pressure is only 2%, initially when the density is less than about million grams per cubic centimeter, gas pressure calculated from Boyle's law is greater than degeneracy pressure, therefore gas will be classical. But beyond this density, you notice that the pressure calculated by Boyle's law is less than the pressure calculated according to Fermi-Dirac statistics, and therefore the gas will be degenerate. This is what happens to the helium core in a star like the sun and in intermediate mass stars. This is what happens to the carbon core in intermediate mass stars. Now let us increase the percentage of radiation pressure till it reaches the magical value of 9.2%. Then you see that as long as you're at a density less than where this dashed line is meeting, where my cursor is, then the gas pressure calculated according to Boyle's law is greater. In other words, the dashed red line is above the blue line, therefore gas is classical and ideal. But above this density, the gas is the pressure calculated according to Boyle's law and the pressure calculated according to Fermi-Dirac statistics are numerically equal, and they remain equal regardless of how high the density may be, because both are proportional to rho to the power 4 by 3. So in a log P log rho plot, the two lines will be coincident. Now let us go to a star which is slightly more massive, so that the radiation pressure is a little more than 9.2%. For example, is 50%. There you see, this red line is the pressure calculated according to Boyle's law, this formula over there. And that curve is always above the blue curve, no matter how high the density is, because the slope is 4 by 3, the slope beyond this point is 4 by 3 of the blue curve, therefore the gas will remain classical no matter what. So if I go to situation where radiation pressure is 90% and gas pressure is only 10%, gas will remain classical all the way through. So this is the essence of Chandrasekhar's remarkable discovery. So now let us look once again at the log T log rho plot. Previously we were looking at log P, pressure versus log rho. Now we are looking at log of temperature versus log rho. This is the non-relativistic degeneracy pressure line. This is the relativistic degeneracy pressure line. Density to the power 5 by 3, density to the power 4 by 3. To the left, gas is classical. To the right, gas is quantum mechanical. So let us consider a core of a massive star. It is classical. It is compressed. Its density increases, but it remains above this line. It is compressed even further in the next stage of nuclear burning. It is still above. It is still classical, and all the way. So massive star, the core remains classical and ideal. Even though the density is continuously increasing, at Each stage of nuclear burning, when the fuel is exhausted, the core is compressed and the density is increasing, but the gas manages to remain classical because radiation pressure continues to be more than 9.2% of the total pressure. But on the other hand, if you are considering a lower mass star, yes, initially the core is classical, but as the density increases, at some stage it becomes quantum mechanical, and then it becomes eventually a white dwarf. So this is the last sentence of Chandrasekhar's historic papers. Unfortunately, even though this is one of his most profound contributions to physics, this paper is not known very much. It is neither quoted nor read much. So let me read it out for you. For all stars above a critical mass, the perfect gas equation of state does not break down, however high the density may become, and the matter does not become degenerate. An appeal to Fermi-Dirac statistics to avoid the central singularity cannot be made. This was one of the most profound statements made in physics in a long, long time. As we shall see later on, this statement signaled that massive stars have no option but to become a black hole. But we'll come to that story later on. So to summarize, in massive star, the core remains classical even though the density increases. Why? Why does the radiation pressure remain greater than 9.2% of the total pressure? Why doesn't the cooling of neutrino cool the core, bring down the radiation pressure below this 9.2% and make the gas quantum mechanical? This is what happened to our carbon core. Initially it was classical, then the cooling due to neutrinos made it degenerate. Now, as I said in the previous lecture, neutrinos are produced in all sorts of reactions. In the unified theory of weak and electromagnetic forces due to Weinberg, Salam, and Glashow, a theory for which they got the Nobel Prize for Physics. For example, in this unified theory, electrons and positrons can collide and produce a neutrino-antineutrino pair. Photons can decay to neutrino and antineutrino pair. Plasma can decay to neutrino-antineutrino pair. Bremsstrahlung, when an electron collides with the nucleus, it can produce neutrino-antineutrino. So at high density and high temperature, as we saw when we discussed the intermediate mass stars in the previous lecture, neutrinos are produced in enormous number by a variety of processes. These neutrinos have very long mean-free path. They just escape the stars. I told you mean-free path of a neutrino, even at density of lead, is several light years. And these neutrinos carry away energy and entropy, and they will core the cool. They will cool the core, So why doesn't the radiation pressure decrease below 9.2% of the total pressure and make the gas degenerate? That answer can only be given by actual detailed calculation. And this plot is derived from this calculation. Now let me explain this. What is plotted on the y-axis, increasing vertically, in logarithmic unit, is the energy generation due to fusion reactions. Energy generation due to fusion reactions is increasing vertically. What is plotted in the x-axis is temperature in units of billion degrees. So this is 10 to the power 9 Kelvin, and so on. Now there are two sets of lines there. This curved line is the neutrino production rate as a function of temperature. So as the temperature of the core increases in the later and later phases of the nuclear cycles, more and more neutrinos are produced. more and more neutrinos are produced. So it's all the more surprising why these neutrinos don't cool the core and bring down radiation pressure. As I said in the previous lecture, it is a competition between cooling due to neutrinos and heating due to energy production in the core. Now let us consider carbon fusing to form oxygen. The reaction rate for carbon to fuse to form oxygen as a function of temperature is very steep. And that is this curve over there. But nevertheless, what you see is that as I go to higher and higher temperature, the neutrino production rate exceeds the heating due to carbon being converted to, the other way around. The heating due to carbon being converted to oxygen is greater. Heating is greater than the cooling. This curve is above this curve. Similarly, when neon is fused, the heating curve is above the cooling curve. When oxygen is fused at a temperature of 1 billion degrees, again, beyond this temperature, the heating curve is greater than the cooling curve. But when it comes to the silicon core, when I fuse silicon, I form iron 56 with a little bit of nickel and cobalt. Then you see, suddenly, the neutrino cooling can become significant and radiation pressure can suddenly come to less than 9.2% of the total pressure, and the iron core can now become degenerate. So by then we have reached the end of our nuclear cycle. By the time silicon burning happens in a quiescent fashion, because once again you see the heating due to silicon fusion, this curve is above the cooling curve. So when silicon is fused, it is fused in a classical regime. So there is no stellar explosion. So this massive star has survived carbon detonation, neon detonation, oxygen detonation, silicon detonation, and it has safely reached the final act of the nuclear drama, which is the production of iron 56 nuclei, the most stable, the most tightly bound nucleus of them all. So you will have an onion skin structure right near the very center of the star. And this is where the story ends, because iron 56 is the most stable nucleus. Now, let us look at how long it has taken to produce these onion skin layers. As I told you, the star spends most of its lifetime on the main sequence, converting hydrogen to helium. So if I am considering, say, a 25 solar mass star, of course, a star like the Sun spends billions of years on the main sequence. The Sun has already spent 5 billion years on the main sequence, and it will spend another 5 to 10 billion years on the main sequence. But remember Eddington's mass-luminosity relation and mass-lifetime relation. A star of 25 solar mass is relatively short-lived. It only lives for about 10 million years or so. Out of that, it has spent 7 million years converting hydrogen to helium, almost 1 million years converting helium to carbon. Carbon to oxygen takes only a few hundred years. Oxygen to silicon takes only a few months. And the final act of the stellar drama, when silicon is converted to iron, happens in about 8 to 10 hours. Can you believe a star has lived for 10 million years? And the final act of the drama is only 8 to 10 million years. 8 to 10 hours, 8 to 10 hours. And then it'll do something very dramatic. So within a matter of few hours, this iron core which is formed and which has now become degenerate. Why does it become degenerate? Because the cooling due to neutrinos now far exceeds any heating. In fact, there is no heating. Iron core is degenerate. Iron core will not fuse by itself. and so it will become degenerate. So the mass of this iron core will grow very dramatically, very, very fast, because silicon is being converted to iron in a matter of hours. And at some stage, it will become degenerate. The size of this iron core will only be about 1,000 kilometers. A 25 solar mass star will have a radius of about 25 million kilometers. But we are talking about a core which is only about 1,000 kilometers. Its density is 10 to the power 10 grams per cubic centimeter, and its temperature is approximately 10 to the power 10 Kelvin. Now, this iron core is inert because there is no energy generation due to fusion reaction. The very large luminosity of neutrinos will make sure the core will become degenerate. And when in a few hours, the mass of this degenerate iron core will grow to this magical mass of 1.4 solar mass, which is known as the Chandrasekhar limiting mass for relativistically degenerate stars. When the degenerate core mass grows to the Chandrasekhar limiting mass of 1.4 solar mass, it will collapse in a matter of a couple of milliseconds. A neutron star will form right at the center. The gravitational binding energy, Gm squared over R released, will be so enormous that it will blow up the rest of the star and you will have a supernova explosion. So the core will collapse. The result of the collapse will be the formation of a neutron star whose size will be only about 10 kilometers now, and the binding energy released will be of the order of 10 to the power 53 ergs, which is more than the gravitational binding energy of the star, and therefore the star will be blown apart. This is a star that was well studied by astronomers in the Large Magellanic Cloud, the galaxy nearest to us. On the 23rd of February 1987, this star exploded. This explosion was seen by a car mechanic in New Zealand, and he alerted all the observatories around the world, and this is a photograph taken by the Anglo-Australian Observatory. In 1968, a neutron star right at the tip of this arrow was discovered in this still expanding debris of a stellar explosion that occurred in July 1054 AD. So this is the final proof that massive stars end their lives by collapsing to form neutron stars, and the gravitational energy blows up the rest of the star. To conclude our discussion of the life history of stars, let us have a very quick recap. Now, what we are going to discuss is merely the end states of stars. And I have stars of various masses stacked up over there, the masses of the stars increasing as I go from left to right. Let us consider first stars whose masses are less than about 9 solar mass. It may be 8 solar mass, it may be 10 solar mass, but of the order of 9 solar mass. How do they end their lives? Well, they end their lives by becoming white dwarfs, which we have not yet discussed, but which we shall discuss in considerable detail rather soon. If you are dealing with stars whose mass is less than half a solar mass, then they will become white dwarfs, yes, and the white dwarf will essentially consist of helium, which is the result of fusing hydrogen. But if you are considering stars in the range between half a solar mass to about 9 solar mass, which will include the sun, then yes, they too will become white dwarfs, but they will become carbon-oxygen white dwarf. It's mostly carbon with a little bit of admixture of oxygen. And what about stars more massive than 9 solar mass or so? Their radiation pressure has always remained more than 9.2% of the total pressure. keeping the star in the classical regime so that the nuclear drama went till the final act. The iron core was produced. The iron core became degenerate due to neutrino cooling. Its mass grew within a matter of hours to the Chandrasekhar limiting mass of 1.4 solar mass. It collapsed, resulting in the formation of a neutron star accompanied by a supernova explosion. Now we shall return to the story of formation of neutron star and supernova explosion and discuss them in considerable detail. I know that's the sort of thing that you people are turned on by. But before that, we must digress. We must digress to refresh our memory about the results of Einstein's special theory of relativity. And then also have some feeling of what the general theory of relativity is all about. Because by the time we reach white dwarfs, we will be dealing with stars which are relativistic. So we must understand special relativity properly. And by the time we go to neutron stars, long before it becomes a black hole, general relativity becomes important. So we must have some understanding. Therefore, I propose to devote the next 2 lectures to this topic. The next lecture will be a review of the special theory of relativity, and the following lecture will be not on the mathematical theory of general relativity, which is beyond the scope of this course of lectures, but the physical content of the general theory of relativity. Thank you very much.